Students often seek a deeper understanding of the various concepts in physics. From classical mechanics to quantum theory, it offers insights that illuminate phenomena ranging from everyday occurrences to cosmic events. Study of physics not only enhances scientific literacy, but also fosters critical thinking, enabling students to explore the captivating interplay between matter, energy, and the fundamental laws governing our reality. So let us explore the world of physics now.
Dear students, in this video we are going to study about resonance in RLC series circuit, the applications of resonance, and also about quality factor, otherwise called as Q factor. The important application of RLC circuit in series is resonance in that series RLC circuit. What is that? We will see now. When the frequency of the applied alternating source omega is equal to the natural frequency 1 by root LC of the RLC circuit, the current in the circuit reaches its maximum value. Then the circuit is said to be in electrical resonance. Therefore, this frequency at which the resonance occurs, that is expressed as omega r, that is called as the resonance frequency. And the frequency at which resonance takes place is called the resonant frequency, that's given by omega r. Now, this is the summary of results of AC circuits, the types of impedance such as resistance, inductance, capacitance, and all the components. The value of impedance is given by this R for resistance, XL for an inductance, L, that's given by omega L, and for the circuit which contains a capacitance only, the value of impedance is given by XC, that's equal to 1 by omega C. When all the three components are connected in series, then the value of impedance is given by root of R square plus omega L minus 1 by omega C the whole square. And what's the phase angle of the current with voltage? That's given by, for resistance only is 0, and the power factor is 1, and for inductance only circuit, the phase angle of current with voltage is 1 by 90 degrees, and that lags. And therefore the power factor is 0, and for only a capacitance, the phase angle of current with voltage is 90 degrees leading, and power factor is 0. And for all the three components, the phase angle of current with the voltage is between 0 degree and 90 degrees, that will lag or lead. And the power factor is given by the value between 0 and 1. Now, the resonant angular frequency omega r, that's given by 1 by root LC. Therefore, the resonant frequency Fr is equal to 1 by 2 pi root LC, and at series resonance is omega r equal to 1 by root LC, and squaring on both sides we have 1 by LC, that's equal to omega r square, and omega r L is given by 1 by omega r into C, or XL is equal to XC. So this condition is for resonance in RLC circuit. That means the value of XL should be equal to that of XC. And since these two values, XL and XC, are frequency dependent, the resonance condition XL is equal to XC can be achieved by varying the frequency of the applied voltage. Now let us see what are the effects of series resonance. When series resonance occurs, the impedance of the circuit is minimum and is equal to the resistance of the circuit. As a result of this, the current in the circuit becomes a maximum. This is shown in the resonance curve, which is drawn between current and frequency, as shown in this figure. And at resonance, the impedance is given by Z equal to root of R square plus XL minus XC the whole square, and that's equal to R, as XL is equal to XC. So this is the resonance curve, and for small values of resistance R, current will be maximum, and for large values of R, the value of current will be less than that for a particular frequency called as resonant frequency Fr. Then this current in the circuit is given by Im, that's the maximum value of current, that is given by Vm by root of R square plus XL minus XC the whole square, and as XL is equal to XC, this XL minus XC becomes 0, therefore Im will be equal to Vm by R. The maximum current at series resonance is limited by the resistance of the circuit. And for smaller resistance, a large current with sharp curve is obtained, and vice versa. Now let us see what are the applications of series RLC resonance circuit. These RLC circuits may have applications like filter circuits, oscillators, voltage multipliers, etc. And an important use of series RLC resonance circuit is in the tuning circuits of radio and TV systems, as you would have seen already. The signals from many broadcasting stations at different frequencies are available in the air, and to receive the signal of a particular radio station, we have to tune the circuit. That is what we call it as tuning the radio circuit. The tuning is commonly achieved by varying capacitance of a parallel plate variable capacitor, thereby changing the resonant frequency of the circuit. The resonant frequency is nearly equal to the frequency of the signal of a particular station. The amplitude of the current in the circuit is maximum, thus the signal of that particular station alone is received. So this is how we are able to listen to any particular radio stations which are broadcasting in that particular frequency. Now let us see what is a quality factor or Q factor. The current in a series RLC circuit becomes maximum at resonance, and due to increase in current, the voltage across L and C are also increased. This magnification of voltages at series resonance is termed as Q factor. And how will you define this Q factor? That is defined as the ratio of voltage across L or C at resonance to the applied voltage. The Q factor is given by voltage across L or C at resonance by applied voltage. And at resonance, the circuit is purely resistive. Therefore, the applied voltage is equal to the voltage across R. And Q factor is given by XL by R. That's equal to omega or L by R. That's equal to 1 by L by R root LC, as we get omega R equal to 1 by root L. Therefore, the Q factor is given by 1 by R into root of L by C. What's the physical meaning of this Q factor? The physical meaning is that the Q factor indicates the number of times the voltage across L or C is greater than the applied voltage at resonance.